Threesome looks like a problem that needs three nested loops. But with the right trick, we can solve it with just 2 pointers. In the previous video on container with most water, we explored one of the most interesting applications of the 2 pointers technique. Before we move on to the next pattern, I want to cover two more classic problems that build on the same idea. The first one is threesome, which we will solve in this video, and the next one will be trapping rainwater. Both of these problems appear very frequently in coding interviews and are great for strengthening your understanding of 2 pointers. Now, let's start with threesome. At first glance, this problem looks quite difficult. You might think we need to try every combination of three numbers, which would take n cube time. But there is actually a clever trick. Using the 2 pointer technique, we can reduce the complexity to n squared and solve the problem much more efficiently. That's why many people consider threesome a capstone problem for mastering 2 pointers. So let's break it down step by step. Now let's understand the problem statement for the threesome problem. We are given an array of integers called nums, and our goal is to find all unique triplets in the array such that a plus b plus c equals 0. There are a few important clarifications. First, the three numbers must come from different indices in the array, so we cannot reuse the same element. Second, the solution set must not contain duplicate triplets, meaning each combination should appear only once. And finally, order does not matter. For example, -1, 0, 1 and 0, -1, 1 represent the same combination. So we include it only once. So our task is simple. Find all unique combinations of three numbers whose sum equals 0. Now a straightforward idea would be to check every possible triplet in the array. But that approach quickly becomes inefficient. So next, let's understand why the naive approach is not enough. Now that we understand the problem, the first idea that might come to mind is a brute force or naive approach. We could simply try every possible triplet of numbers in the array and check whether their sum equals 0. To do this, we could use three nested loops. The first loop picks the first number I, the second loop picks the next number j, and the third loop picks the final number k. So essentially, we are checking every combination of I, j, k. However, this approach quickly becomes expensive. Because we are using three nested loops, the time complexity becomes n cube. For a very small array, this might seem manageable. For example, if n equals 6, there are only about 20 possible triplets. But as the array grows, the number of combinations increases dramatically. If n equals 100, we already need to check around 166,000 triplets. And if n equals 1000, the number jumps to around 166 million combinations. At that scale, the brute force approach becomes too slow for practical use. So instead of checking every possible triplet, we need a more efficient strategy. And the key idea is to reduce the three-sum problem into a two-sum problem, which will allow us to use the two-pointer technique to significantly reduce the time complexity. Let's see how that works. Now let's look at the key idea that makes this problem efficient. We are given the condition a plus b plus c equals 0. Instead of trying all possible triplets, we can simplify the problem. First, we fix one element from the array. Let's call this element a, which is nums I. Once we fix a, the equation becomes b plus c equals minus a. So the problem is now reduced to finding two numbers in the remaining array whose sum equals minus a. In other words, 3 sum becomes a 2 sum problem after fixing one element. For example, suppose nums I equals minus 1, then minus a equals 1. So our new task is simply to find two numbers whose sum is 1 in the rest of the array. If we find such a pair B, C, then together with A, they form a valid triplet that sums to 0. This reduction is the key insight that allows us to avoid checking every possible combination. But to efficiently find this pair using the two-pointer technique, there is one important requirement. The array must be sorted. So next, let's understand why sorting is necessary for this approach. First, consider the case where the array is not sorted. Suppose we try to place two pointers at the ends of the array, one on the left and one on the right. If we calculate the sum and realize that we need a smaller sum, we naturally want to move one of the pointers. But here is the problem. Because the array is not ordered, we cannot confidently decide which pointer to move. Should we move the left pointer or should we move the right pointer? Since the numbers are arranged randomly, moving either pointer might increase or decrease the sum unpredictably. So the pointer movement becomes unclear and unreliable. Now let's see what happens when the array is sorted. When numbers are arranged from smallest to largest, the behavior becomes predictable. If the current sum is too small, we know that moving the left pointer to the right will increase the value and potentially increase the sum. If the current sum is too large, we move the right pointer to the left to reduce the value and decrease the sum. Because the numbers follow an ordered structure, every pointer movement has a clear logical purpose. So, sorting the array gives us a reliable rule for pointer movement. And once the array is sorted, we can now set up the two pointers properly to start searching for valid triplets. Next, let's see how we initialize the pointers for the two-pointer search. Now that the array is sorted, we can set up our pointers. For each position I, we treat that element as the first number of the triplet. Then we search for the remaining two numbers in the rest of the array. To do that, we initialize two pointers. The left pointer starts at I plus 1, which is the element immediately after I. The right pointer starts at n minus 1, which is the last index of the array. So now we have three positions. I, the fixed element, left, searching from the beginning of the remaining subarray, right, searching from the end of the remaining subarray. Our goal is to check whether the sum of these three numbers equals 0. Since the array is sorted, we can intelligently move the left and right pointers to adjust the total sum. So, for each fixed I, we perform a two-pointer search on the remaining sorted subarray. Next, Let's understand how these pointers move depending on the sum we get. For every position of I, we compute the current sum using three elements: nums I plus nums left plus nums right. Then we apply simple movement rules. If the current sum is less than 0, it means the total is too small. Because the array is sorted, we can increase the sum by moving the left pointer to the right. So we do left plus plus. If the current sum is greater than 0, the sum is too large. To reduce it, we move the right pointer to the left, which means right minus minus. If the current sum becomes exactly 0, we have found a valid triplet. So we record the triplet and then move both pointers inward, left plus plus and right minus minus, to continue searching for other possible pairs. This strategy works because the array is sorted. Moving the left pointer increases the sum and moving the right pointer decreases the sum. Now let's walk through a step-by-step example to see exactly how these pointer movements help us find the triplets efficiently. Our sorted array is -4, -1, -1, 0, 1, 2. Assume the current index I is pointing to -1 at index 1. We now place our two pointers, left at the position next to I, that is index 2, and right at the end of the array, index 5. Now we compute the sum, nums I plus nums left plus nums right, which is -1 plus -1 plus 2. This gives us 0. Since the sum equals 0, we have found a valid triplet -1, -1, 2. After finding a valid triplet, we move both pointers inward to search for other possible pairs. So we do left plus plus, right minus minus. Now we check the new pair. After moving both pointers, the positions update. Now I is still at -1, left moves to 0, right moves to 1. Now we compute the sum again. -1 plus 0 plus 1. This again equals 0. So we find another valid triplet, -1, 0, 1. Once again, we move both pointers inward, left plus plus, right minus minus. Now the left pointer crosses the right pointer. This means the inner two pointer search for this index I is complete. So we move to the next index of I and repeat the same process. Now let's understand what happens when we move to the next value of I. In the first iteration, I equals 0 and nums I equals -4. We set our pointers like this. Left equals I plus 1, right equals n minus 1. So here left equals 1 and right equals 5. Now we search for two numbers between these pointers such that nums left plus nums right equals 4, because -4 plus pair equals 0. After we finish checking all pairs for I equals 0, we move to the next index. Now I equals 1 and nums I equals -1. At this point, we reset the pointers again. Left equals I plus 1, right equals n minus 1. So now left equals 2, right equals 5. Notice something important. All elements before I are already processed. So we only search in the remaining subarray to the right of I. That is why the pointers must be reset for every new value of I, so that we can explore all possible pairs in the remaining part of the array. In the next step, we will look at another important detail in the three-sum problem: how to avoid duplicate triplets. To clearly understand how duplicate triplets can occur, let's look at another example. Here we have the sorted array -2, 0, 0, 2, 2. Notice that the array contains duplicate zeros and duplicate 2's. If we fix -2 as our first element and run the two-pointer search, we find the triplet -2, 0, 2. After finding a valid triplet, the algorithm moves both pointers inward, left plus plus and right minus minus. But because there are duplicate values in the array, the pointers can move to the next 0 and the next 2, producing the same triplet again. Even though the indices are different, the values forming the triplet are identical. Since the problem requires unique triplets, we must skip duplicate values during the algorithm. In the next slide, we will see how the algorithm handles duplicates to avoid repeating the same triplet. We skip duplicates in three specific places. First, when selecting the fixed element I. If the current value is the same as the previous one, it means we already processed this number as the starting element. So, we simply skip it. This prevents starting the search with the same value again. Next, after we find a valid triplet, we also skip duplicate values on the left pointer. If the next value on the left is the same as the previous one, we keep moving the pointer forward. Similarly, we skip duplicate values on the right pointer. One important thing to remember is that duplicate skipping happens only in two situations: when selecting the fixed element I and after we find a valid triplet. We do not skip duplicates during normal pointer movement because that could cause us to miss valid combinations. Now that we understand how duplicates are handled, let's put everything together and look at the complete algorithm step by step. First, we sort the array so that we can use the two-pointer technique and easily handle duplicates. Next, we iterate through the array and treat each element as the fixed element of the triplet. To avoid duplicate triplets, we skip the iteration if the current element is the same as the previous one. For every fixed element, we initialize two pointers, left at the next position and right at the end of the array. Then while left is less than right, we compute the sum of the three elements. Depending on whether the sum is less than 0, greater than 0 or equal to 0, we move the pointers accordingly and record valid triplets. Now that we understand the full logic, let's move to the actual implementation. Now let's look at the actual implementation of the three-sum solution in Python. The problem asks us to find all unique triplets in the array whose sum equals 0. Notice that the solution set must not contain duplicate triplets. For example, if the input array is -1, 0, 1, 2, -1, -4, here valid triplets are -1, -1, 2 and -1, 0, 1. Also, the array size can be up to around 3000 elements. So a brute force approach O(n) cube solution would be too slow. Instead, we use a more efficient strategy using sorting and the two-pointer technique. So first, we sort the array. Sorting allows us to apply the two-pointer approach efficiently and also makes it easier to identify duplicate values. Now we will iterate through the array. For each index I, we treat nums I as the first element of the triplet. We iterate until n minus 2 because we still need 2 additional numbers to form a triplet. We also include a small optimization. If nums I becomes greater than 0, we can stop the loop early. Since the array is sorted, all remaining values will also be positive, and 3 positive numbers cannot sum to 0. So in that case, we simply break out of the loop. Next, we check for duplicate starting values. If the current element is the same as the previous element, we skip it to prevent generating duplicate triplets. Now we initialize 2 pointers. Left starts at I plus 1 and the right pointer starts at the end of the array. While left is less than right, inside this loop we will calculate the current sum. If the sum is less than 0, we move the left pointer forward. If the sum is greater than 0, we move the right pointer backward. If the sum becomes exactly 0, we have found a valid triplet. So we add nums I, nums left and nums right to the result list. Let's declare it. Now add the nums I, nums left and nums right to the result list. Then we move both pointers inward. Here we are skipping the duplicate from the left. Here we are skipping duplicate from the right. Now we return the result. Let's run the code. It ran successfully and passed all the test cases. Let's submit it. It submitted successfully as well. Now let's analyze the time and space complexity of this algorithm. First, we sort the array before starting the search. Sorting takes O n log n time. Next, we run an outer loop where we fix one element I. This loop runs n times, so its complexity is O of n. For each fixed element, we perform a two-pointer search using the left and right pointers. In the worst case, these pointers scan the remaining portion of the array once, which takes O(n) time. So, for each element, we perform a linear scan. This means the total work becomes n cross n, which results in O(n) square time complexity. The initial sorting step O(n) log n is smaller compared to O(n) square, so it does not dominate the overall complexity. Therefore, the final time complexity of the optimized three-sum solution is O(n) squared. Next, let's look at the space complexity of this algorithm. The algorithm only uses a few variables during execution. We maintain the index I for the outer loop along with the left pointer and right pointer for the two-pointer search. We also use a variable to calculate the current sum of the three elements. These are just a constant number of variables and they do not grow with the size of the input array. Because of this, the extra space used by the algorithm is O of 1, which means constant space. Also note that the output list of triplets is not counted when calculating space complexity because it is part of the required result. So the space complexity of this approach is O of 1. Next, let's quickly summarize the key takeaways from the three-sum algorithm. First, we sort the array. Sorting is essential because it allows us to use the two-pointer technique efficiently and also helps us handle duplicates easily. Next, we fix one element which we call nums I. This element becomes the first number of our triplet. Then we use two pointers, left and right, to search for the remaining two numbers that complete the triplet. Depending on the sum we calculate, we move the pointers accordingly. If the sum is too small, we move the left pointer forward. If the sum is too large, we move the right pointer backward. Whenever the sum equals 0, we record that triplet as a valid solution. And finally, we skip duplicate values to make sure we do not produce repeated triplets. So in simple terms, the idea is fix one element and solve the remaining part as a two-sum problem using two pointers. Now that we understand the complete workflow, let's look at the pattern behind this solution, the two-pointer technique. Before we wrap up, let's recognize the key pattern behind the three-sum solution. The idea is simple. Fix one element and use the two-pointer technique to find the remaining pair. First, we sort the array, then fix a number, and finally move the left and right pointers to search for the pair that completes the target sum. This pattern appears in many problems like two-sum in sorted arrays, three-sum, four-sum, and closest three-sum. More generally, many k-sum problems follow the same rule. Fix k-2 elements and solve the rest using two pointers. Recognizing this pattern makes these problems much easier to solve. If this explanation helped you to understand the concept clearly, consider liking the video and subscribing for more structured DSA explanations. And in the next video, we will explore another classic two-pointer problem, trapping rainwater, where we use pointers in a different way to calculate how much water can be trapped between bars. If you understood the two-pointer idea here, the trapping rainwater problem will feel surprisingly intuitive. Thanks for watching, and I will see you in the next video.